So our project was on finding the lattice structure of gold by using Fourier transformations. Just as a brief introduction to X-ray diffraction, it's used mainly in chemistry and material sciences on materials that are too small to be seen within microscopes and materials that would be disrupted by visible light because of the larger wavelength. So what they do is they shoot a crystal with X-rays in a goniometer, and those X-rays then bounce through the lattice structure to give a diffraction pattern. So you can see here in the bottom right, which is the concentric rings. This is what happens when those lattice structures don't fully overlap. You can see here that once you get these rings, you can then interpret them into coordinates and then apply a filter transform to those coordinates and a filter, and that will then produce the density and structure of that crystal. This technique was discovered by William Henry Bragg, who discovered that the destructive and constructive interference of the crystal is directly proportional to the reflected angle. So if the angles are equivalent, then you will get this sort of structure here you can see here on the left hand side, and this can be represented by n lambda, which is equal to 2d sine theta, where n is a positive integer, lambda is the wavelength, d is the distance between the lattice structures, and theta, of course, is that angle. Pictured here is an area diffraction pattern. This specific one is for gold. Pictured here is an area diffraction pattern. This specific one is for gold. A lot of the coordinate data is hosted on Linux clusters, which means that access to it is very limited. So instead, you have to take the images of the diffraction patterns like you have here and use applications to then analyze those pictures. So in our specific case, we use the MATLAB add-on. So this is the MATLAB add-on diffract index. We uploaded that gold diffraction pattern into it. It then analyzes the pixel size of the image, and you can then label the positions on the innermost ring and then continue on with each of the rings after that. It will then interpret those coordinates into intensity versus radius, and then again into a matrix that is easier for MATLAB to use.
Using diffract index, we can obtain data on intensity versus coordinate places and intensity versus radius. They are interchangeable, and here to make it easier to visualize, we have a graph of intensity versus radius on the left. As you can see, the peaks on the graph correspond to the rings in the diffraction image. These peaks get smaller as radius increases due to there being a smaller amount of X-rays being diffracted there. To find where individual lattice points are located for the structure, however, we need to first do the Fourier transform on both x and y dimensions. This takes us to the reciprocal space. The transform data is shown on the graph to the right. Note that this is harder to visualize because the image is a slice of a much larger array. We then apply a low-pass filter to the data as shown in the graph. The Fourier transform data is colored blue, and the filter is colored orange. Note that this filter must have a similar periodicity to the points within the direct lattice, and this relates to the crystal structure of gold. That way, the inverse Fourier transform data would tell us where the individual lattice points are located for gold. So we then do the inverse Fourier transform, which reveals a function with peaks around lattice points, as shown in the graph on the right. There were 5 noticeable rings within the gold diffraction image, and this set shows us 5 different peaks corresponding to those lattice points.